Hello, I'd like to go over some of the frequently asked questions about the homework for Unit 5 Module 2 and to go over some of the elements of the pop quiz that's covered Unit 5 Module 1 and up to the extent, quantifying the extent in Unit 5 Module 2. Okay, so here are two types of questions that are quantitative. We are going to use the relationship of delta G and K. We have this expression here, where R is 8.314 joules per mole Kelvin. And then if we're given K and we need to calculate delta G, we can use the equation delta G equals minus RT ln K. And so just depending on what kind of initial information you're given, of course both of these equations will be given to you on the exam. These are the two equations you need to use if you're given one and you have to calculate the other. Okay, so we plug in the number. Keep in mind I'm going to use R in joules. Of course you could use kilojoules, but I'm using joules, so I multiply delta G by 1,000. Put in the numbers. The temperature is at 298. If I do that, plug that in the calculator, I get 7.8 times 10 to the minus 6. So this is definitely reactant favored, K is less than 1, and delta G is positive. Let's take a look at the bottom problem. Here we write the expression. We're not given K in terms of numerically directly. We have to find it from the equilibrium pressures that are given. So we write the expression, remember products over reactants. These are products. This is Kc. But we're given the pressures, so I'm going to write Kp. So the pressure of C to the 1 power, pressure of D squared, divided by the pressure of A cubed, divided by the pressure of B squared. Now, if I know the equilibrium expression, if I know the equilibrium pressures, I can plug them in, which I'm going to do here, and then calculate K. I do that and I get a value of 0.0297. That's what K is equal to. Now put in the formula. Since I know the temperature, I know R, now I know K. If I do that, I get a value of delta G. This value is in the units of the R I'm using in terms of joules. Get 8,713 joules per mole. The answer asks for kilojoules per mole, so I divide that by 1,000 and I get 8.71 kilojoules per mole. So if you can't see the dot, it's 8.71 kilojoules. So you just want to make sure that you can, given one of either K or delta G, you can calculate the other. Okay. Next. Here we have, so a picture will help with this problem. So here we have silica gel, and there's a bunch of water out in the atmosphere. We'll call that the reactants. And then when they react, meaning that water is absorbed onto the silica, it looks something like this. So this is these are the two states, reactants, let's say, and products. So it's clear that the water is a lot closer to the silica in the products. And so if that's the case, we would say the products have lower potential energy, and so delta H would be less than 0. We also see that the particles are much closer, meaning there's a lot less configurations because the water in the atmosphere is now sticking to the silica. So delta S is also less than 0 for this process. So we would pick these two answers. And then based on the language of the problem saying that water vapor readily absorbs onto it, we would expect this to happen as a product favored reaction, readily absorbs, spontaneous, delta G less than 0. Okay, so this problem is always kind of tricky to think about, but a picture helps analyze it well. Here, this is a lot like the problem we had in the pop quiz. We're given delta H and delta S, and we're asked under what conditions, under what temperatures, is the reaction spontaneous or product favored. So delta H and delta S are both positive. So we draw the delta G versus T curve for that. and we see that product favors happens at high temperatures. So once we solve for the critical temperature, we just say that this is going to happen at temperatures greater than that one. So we calculate the critical temperature by taking the ratio of delta H to delta S. We divide them, and the critical temperature here turns out to be 533 Kelvin. So we would expect temperatures greater than 533 Kelvin that we would have product favored. So that means we go from K greater than 1, that would occur right at 533, and that at 533 the delta G versus T is when delta G becomes less than 0. Alright, here's a series of reactions, and they're asked which ones are going to be product favored. So just for practice, we'll go through all the delta H and delta S designations. The first one definitely is exothermic. We have AA bonds as reactants. We also have a gas getting converted into solid, so delta S is less than 0. The second one, we have two particles making one. That's definitely exothermic, and gases going to solid, also delta S less than 0. We have a solid going in, breaking apart into two particles. We would expect this to be greater than 0, and then delta S to be greater than 0. Here we have the combustion of hydrogen, AA bonds in the reactants. That's definitely going to be exothermic. 3 gas particles making 2, delta S less than 0. Here we have AA bonds in both cases, so we use secondary considerations. Solid and liquid in the reactants, we would pick this as endothermic. Secondary conditions. And then gases being made, delta S is definitely greater than 0. And then the last one, we have AA bonds in the reactants, so this is definitely exothermic. And we have 3 gas particles going to 1, so delta S less than 0. But the question asks about product favored just from delta G, and just from delta G in the sign, we can assign these 3 to be product favored. So you should be able to walk through reactions like this without any problems. Alright, in this question, what we have to identify is what does it mean by something that's always reacted favored? Well, that means that R is down in the bottom right. If something's always product favored, then P is in the bottom right. And if we don't have enough information, we either have two cases, right? Where we have these positive diagonals, where either we have delta H and delta S with the same sign, it could be positive, or delta H and delta S both being negative, right? And now we just need to assign which one of these reactions are which. So let's do that. So here we have delta H less than 0, but delta S greater than 0. And here delta H greater than 0, but delta S less than 0. So when they have different signs, they're in the always never category. Alright, so not enough information is when they have the same sign. That occurs with the two gas molecules of A reacting with 3 gas molecules of B to make 4 gas molecules of C. We get an exothermic reaction and the entropy decreases. We also have that in the reaction of A and B as gases reacting to make 3 gas particles. Delta H here was given as positive, and delta S here is positive as 2 gas particles make 3. So always reactant favored would be this particular reaction where you have 3 gas particles making 1, so delta S is negative, and delta H is given as positive. And the last one, we have A solid plus B gas making 2 gas molecules in the C. Delta H is given as negative, but in this case 1 gas particle making 2 gas particles will definitely be delta S positive. Right, so in this particular case, the most important part of this problem is assigning what does it mean to be reactant favored and product favored always, and what do you need more information. Alright, so here we have a PEC diagram, and let's keep in mind that our chart that we've been using, so always never are these 2 boxes, then high temperature favorability and low temperature favorability. Here we see that products are in the always category, so we would definitely pick A, right? Products are always favored. It's in the always category. What are the signs here? Well, we see that R has higher potential energy than P. P has less. Anytime P has less of either potential energy or entropy, the sign is negative. So this is exothermic, delta H less than 0. But P has higher entropy, so delta S is greater than 0, so we would pick B. What reaction given would correspond to this diagram? So we look through it, delta S greater than 0, that's the case for D, as we have to use secondary considerations given that oxygen going to CO2 has the same number of gas molecules, but the products are more complicated and massive, so we'd pick delta S greater than 0, and it's also delta H less than 0, as the products are assumed to be more stable and have lower potential energy. There we can use primary considerations. This type of reaction, AA and BB to make AB, is for us defined as exothermic. If we want to know the temperature range, we first have to calculate delta H, which we do. It's positive 74.8 times 10 to the third joules per mole. Delta S, we do the same thing. We get 80.8 joules per mole Kelvin. And now the critical temperature at which, since they have the same sign, there's a critical temperature at which it becomes reactant favored or product favored. That critical temperature is the ratio of delta H to delta S. And if we do that, we see the critical temperature here is 925 Kelvin. So to find out if it has to be higher or lower, we just sketch a delta H versus delta G versus T curve for positive delta H and positive delta S, and we see that product favored occurs at high temperatures. That's when delta G becomes negative, so that means we need a temperature greater than 925 Kelvin. You're going to have to do these types of analyses on the exam, so it's very important that you feel comfortable with it. Okay, in this problem, we want to calculate delta G from a table of data. First thing we have to do is calculate delta H. We do that for the reaction products. We sum up the products and we subtract them from the sum of the reactants. We do that, we get 247.1 kilojoules per mole. For delta S, we do the same thing. We sum up all of the entropy contributions from the reactants. Keep in mind the coefficients for each one, and then we subtract the sum of the reactants. We do that, we get 256 joules per mole Kelvin. Delta G can be calculated at the temperature 223 Kelvin, which was specified. You do not want to put in minus 50. You want to put in the temperature in Kelvin. And at that temperature, delta H minus T delta S looks like this. You calculate it, and you should get about 190 kilojoules per mole, which would be C. Here we have, now that we have the signs of delta H and delta S, we can find the right E versus S curve. So we know delta H is greater than 0 and delta S is greater than 0. That means P has to have higher potential energy and higher entropy. That puts it in the top right corner. R would be in the bottom left corner. And in that case, since they have the same sign, they're going to be in the positive diagonal, and we would pick A. For delta G versus temperature, keep in mind that the sign of delta H is the value of delta G at T equals 0. So we just put that up there. Delta H is greater than 0. We just put a dot right there on the when T equals 0. And then the slope, which is equal to minus delta S. Delta S is positive. So overall, the slope is negative. That means we would pick B, which is consistent with delta H and delta S having the same sign, which is that they should cross at some temperature. B. Question number 4. So this, we did example just like this in class, but it so what are we trying to do? Well, one of the reactions is that we have iron solid going to make iron oxide, and this is minus 824 kilojoules per mole. We're going to reverse this reaction, and now it becomes positive 824 kilojoules per mole. And that's exactly what we need in the reaction. We need the product of the top reaction given in the table. We need the product as a reactant. If that's the case, we have to reverse, right? We have to reverse the reaction and change the sign. Keep in mind that the overall reaction is multiplied by 2 in the problem, and so we put a 2 times everything here. The second part, titanium solid reacting with O2 to make titanium O2. This is given as minus 944 kilojoules per mole. That is in the right direction, right? We're starting with titanium, making titanium oxide. It's the right direction. It just has a 3 coefficient in front of it, so we multiply by 3. Now we have our overall reaction. We can just add these two together. When we do that, we get something that we get exactly what the reaction above is. And now we just add up our energies. 2 times 824 plus 3 times minus 944. We do that and we get minus 1184 kilojoules per mole, which should be B. So keep in mind, you're often given only formation types of reactions, and so if that's the case, you may have to reverse a reaction and add it together if you're given that type of information. The last question on our pop quiz dealt with ranking entropies. So keep in mind we had O2 minus for all, they're all in common, which means that if O2 minus is present with titanium and there's 2 oxygens, titanium must be plus 4. For iron, it must be plus 3. For barium, it must be plus 2. For sodium, it must be plus 1. And potassium, it must be plus 1. Right? These are the formulas given. This is what we did in class. And so now we say, okay, what are the rules? Well, the lowest charge is always going to have the highest entropy, right? We saw that in the data. And the highest charge has the lowest entropy since it's the smallest. The remaining electrons with the highest charge are held very closely to the nucleus. It's very small. Titanium plus 4 is the highest charge. It has the lowest entropy. And potassium and sodium have the highest charge. So they'll have the highest entropies. If we have to choose between sodium and potassium, if they have the same charge, then we would use mass or numbers of particles. So potassium must have the highest entropy, highest mass. So that would be B, right? You weren't asked to distinguish between sodium and potassium. The main thing was to see that titanium oxide has to have the lowest, and sodium and potassium have to have the highest. Okay, just want to walk through a quick summary, delta H and delta S of potential energy, S, delta G versus T, and K versus T. So this graph here, they're the same sign. We are on the positive diagonal of E versus S. You will cross the line for delta G versus T. Since delta H is less than 0, delta G starts less than 0 and then crosses the axes. K versus T, has to be shown as product favored, meaning K greater than 1 at low temperatures, and that it crosses the axis at some critical temperature and then becomes reactant favored. We look at the other scenario where delta H and delta S have the same sign. P now has higher potential energy and higher entropy, so it's in the top right. You access more products at higher temperatures now. That means delta G becomes negative at higher temperatures, and it means that K becomes greater than 1 at higher temperatures. So you just want to make sure that you can walk through this type of analysis for each one of the different cases. right? And also you want to remember where products are favored. So products are always favored at delta G greater than delta G less than 0 and K greater than 1. All right, the other case here is when delta H and delta S have different signs. That puts it in the always never category. So P here is in the always, meaning delta G does not cross the axis. It starts negative as delta H is less than 0 and stays negative. We also know that as we increase the temperature, we access the reactants, which should lower K. We will never lower K to the extent that we cross the axis, but K should go down with temperature as we increase temperature. Delta H and delta S, the last case, here we have reactants in the always category, meaning delta G at all temperatures is positive. It starts positive because delta H is greater than 0 and then has a positive slope. Since this delta S is negative, the slope is minus delta S, so that would be positive. That's going to have a K versus T where as we increase the temperature, we access the products, but we don't cross over because we don't make more products than reactants because reactants are always favored. So K starts going up but never crosses the axes. All right, with that, you should be prepared for the Unit 5 Module 2 homework and for an analysis of the pop quiz. Please check out the exam materials that are located on D2L, and good luck. Exam 1 will cover Units 5, Module 1 and Module 2 only, up to Module 2. All right.